Spectroscopy is going to be the final piece of our History of Astronomy unit that we're going to be focusing on today and tomorrow. We're going to be dealing with spectroscopy. This video will provide you with a basic introduction into what it is, how it works, and where the information we gather can be useful to astronomers. Tomorrow in class we're going to be doing a spectroscopy lab where you're going to get the full practice of how to do this and how to gather the information from what you're seeing and observing. So first and foremost, you're going to be using a piece of equipment in the lab tomorrow called a spectroscope. Part of your homework tonight will be to watch a pre-lab video that shows you how to use a spectroscope if you've never used one before. I'll do a very quick review of it in class at the beginning tomorrow before we get into the lab as well. But its purpose is to split light sources into the component colors that they are made of. Every single color, red, orange, yellow, green, blue, indigo, violet, and all the shades in between, each have their own unique wavelength and frequency. So when you look at a particular light source with your own eyes, you just see whatever color is radiating out from it. When we look at it with a spectroscope, we're only allowing a certain amount of light to pass through, and it passes through a form of a lens. That lens is designed, it's called a diffraction grating, and it's designed to split up that light source into the component colors that it is made up of. And there are two ways that you can observe spectral lines. The first one is what we call the emission lines. These are the individual frequencies that are given off, or the term we use is emitted, by specific atoms. So if you look at the diagram to the right, if you have a standard light bulb that's illuminated, it's heated up, when that light passes through a prism, or like our diffraction gratings that we'll use, you see an almost complete rainbow. This is what we call a continuous spectrum. That's a continuous spectrum. Now if you take a look at the bottom one, this is a sample of heated up hydrogen gas, and you'll see hydrogen specifically in the lab tomorrow as well. If you've ever seen a neon sign or neon lights before, this is essentially how they work. They are a specific element, or in some cases a compound or mixture, that has electrical current passing through it. It heats up, it gives off some light, but when you use a spectroscope or diffraction grating, it splits up into very specific wavelengths. So hydrogen, as you can see on that little screen, we see one distinct line of red, one distinct line of green, and then a few lines in that blue and violet portion of the visible spectrum. And again, this is very unique to hydrogen. Emission spectrum can be used to identify specific elements within a light source. Best way to think about this, these are like fingerprints for elements. Every single element has its own unique set of emission lines. So hydrogen, again, at the top is the one we probably focus on the most because it is the simplest element and the most abundant, but you can see how distinctly different it is from all these other ones. The ones shown on here, sodium, helium, neon, and mercury, not necessarily all the most common. Helium we deal with a lot. Neon and mercury, a little bit less so, but still are pretty prominent ones. And then sodium is a pretty common one that we'll find as well. But every single element, no matter which one, is going to be unique from all of the rest. On the flip side is the absorption spectrum. If you take a continuous spectrum like we saw with an illuminated incandescent light bulb, a normal light bulb, if you take a continuous spectrum and it passes through some cool gas, atoms of the gas will absorb the exact same frequencies that they actually emit. So you can actually identify what that cooler gas is made of by looking at the absorption spectrum. You can actually see which lines are missing. So if you look at that screen, the continuous spectrum is there minus a few specific wavelengths. You see that there's one in the red and orange area that's missing, a green, and then a few towards the blue and violet. Identifying the ones that are absent can be used just like the emission spectrum. What will end up happening, if you compare the absorption and emission spectrum of the same element, combine the two together, you should get a continuous spectrum. So this one shown here is the emission spectrum on the top, absorption spectrum on the bottom of sodium. Again, those two wavelengths in the yellow spectrum part of the spectrum, those are what's missing in the absorption spectrum. Now, a little bit of some chemistry into what in the world are these wavelengths? What is it? How is this even happening? What's going on? These emission lines correspond to certain amounts of energy. And there are energy differences between the different energy levels that the electrons can take on within the atoms themselves. So if you remember much of your chemistry, the electrons today, as we understand the model, are found in what we call the electron cloud. And there's different likely positions or likely distances that they could be away from the nucleus of the atom. Okay? There are what we call ground states, like you see on the left, where the atom as a whole is largely stable and the electrons are at their lowest possible energy levels. When they get heated up, when energy is put into them, they shift to what we call an excited state. Typically, this means they're, in general, going to move further away from the nucleus of the atom, but they're in a state that's excited and it's unstable. They'll only stay there for a short period of time, and they will drop down to the ground state. When they drop from the excited state to the ground state, they release energy. That energy ends up being released in the form of light. And that amount of energy directly corresponds to specific wavelengths for that particular atom. So that's where we get these different ones. And there are different excited states for each element. There's not necessarily just one. There's always a couple at least, and that's what gives us the different wavelengths that we see. Final part to our introduction into spectroscopy is how do we determine this amount of energy? Okay, so photon is the term that we use for light. Light sometimes acts like a wave, sometimes acts like a particle. It has properties of both, and the term we use today for bits of light, if you will, a packet is the official term. We call them photons. And we can identify and calculate out the amount of energy an individual photon has just by knowing the spectral lines of the element. So the equation that you see here, E equals H times F. E corresponds to the energy. Energy is measured in a unit that we call joules. If you've had physics or remember back to your 9th grade physical science, potential energy, kinetic energy were used, our same set of units was used to measure that. Same thing goes here. Frequency is measured in hertz or waves per second. Now this number is going to be fairly large for specific colors or photons of light. H is a constant called Planck's constant. A physicist named Max Planck developed this based off of these types of observations. And you can see the value there. It's a very, very small number. Realize when we calculate the energy of a single photon, the numbers are going to be pretty small, on the order of times 10 to the negative 19th, times 10 to the negative 20th. You'll get some practice here in a few minutes with calculating these, and we'll do that a little bit more in the lab tomorrow as well. But Planck's constant, 6.63 times 10 to the negative 34th joules times seconds. Now lastly is, in order to find the energy, we do need to know the frequency of each of these colors of light. Now, when we do this in the lab tomorrow, we don't have spectroscopes that tell us the specific frequencies. Our spectroscopes actually tell us the wavelength of light. But if we know the wavelength, we can determine the frequency using this equation here. This is known as the wave equation. This is specific for light. Lowercase c is our speed of light, 3 times 10 to the 8th meters per second, the same number we've been using throughout this term so far. But when we use the spectroscopes tomorrow, we'll be able to measure the wavelength using the spectroscopes. We do, however, need to figure out the frequency. So when you rearrange this equation to solve for the frequency, you're going to take the speed of light, 3 times 10 to the 8th meters per second, and divide by whatever wavelength you happen to get. Wavelength typically will be measured in meters, but wavelengths of light are very small, so oftentimes they are in nanometers. We'll talk about the specific values for that tomorrow, but just know 1 nanometer is equal to 10 to the negative 9th meters. So again, very, very small amount. Now, if you're asking as we go through all this, where does this come into play? Why is this so important for us in astronomy? What this really comes down to is if we look at a star with a spectroscope, which most astronomers today, when they're spending time identifying new stars or objects in space, this is exactly what they're going to do in addition to their telescopes, is they'll use spectroscopes to do some identification. They are looking for the specific wavelengths that make up different elements. So hydrogen is, again, one of the most common. If you look up above, you'll see absorption spectrum from a particular star. And down below you can see the emission spectrum of hydrogen. So we're looking for those lines of hydrogen in the absorption spectrum to be missing. That's an indicator that it is indeed there. If those wavelengths all match up with the vacancies, then we know that hydrogen is part of this. And then there's some additional information even beyond chemical composition. We mentioned this already, like trying to identify hydrogen, helium, other things like that. This can also help us determine the temperature that a star or whatever light source we're looking at might have, but also radial velocity. Now this one comes into play significantly when we start talking about entire galaxies and their movement. Basically, we're looking for certain wavelengths, but if we find a certain combination of wavelengths, say hydrogens, as you can see down here, at rest, those are the wavelengths we should see. But if we're observing, say, a galaxy, and it has all those same wavelengths, but they've all been shifted towards the red side of the spectrum, this particular galaxy is moving away from us. And just the opposite, if they're shifted towards the blue side, they're moving towards us. So even spectroscopy can help us figure out things like that, the movement of galaxies relative to us. And this table just identifies some of those specific things that we can observe and what information they can provide. Finally, this leads us to the homework assignment for you tonight. This worksheet, called the spectroscopy worksheet, is on the Canvas page, under the homework page on Unit 2. The big thing, our questions 5 through 8, is going to be some practice with using these different equations right here. The constants for Planck's constant, h, and c, the speed of light, are listed there for you. Again, wavelength, if you know a wavelength, you can use c equals f times wavelength to figure out frequency, just rearrange. If you know the frequency, that will allow you to find the corresponding energy for a photon. So this will be some practice with it. Be sure to show your work. We'll go over some of this tomorrow prior to the lab. But that is it for your introduction into spectroscopy.